Hey guys, and welcome to Functional Print Friday, and welcome back to my shop. So you guys click the thumbnail. You know we're doing something a bit different this week, and I'm really excited about this video. This is a video that I've wanted to do for a while, because this is primarily a 3D printing channel. Normally I'll show you guys something that I'm trying to fix, something that I'm trying to add a feature to, or even just some problem that I want to solve that is going to take a from-scratch design. And I'll walk you guys through the design and the engineering, my thought process. We'll usually go through a couple different iterations with the design and 3D prints, and then I show you guys the finished solution. Well, 3D printing is not always the end-all be-all, as we've encountered here numerous times on this channel. Sometimes you need subtractive manufacturing to kind of step in and rescue you when 3D printing is just not the right process. And I've got some examples of that here on the bench, and these are all examples where we used a lathe to get one of the components that we needed. Here is a speed handle that I made for my milling machine vise. And all the complex geometry on this we were able to 3D print, and it worked out really well. So this drives the hex shaft on the milling vise, so the hex shaft turns as we crank this around. And on this end, we could have 3D printed a handle, and honestly we could have just printed this solid and let it rotate in our fingers, and it would probably hold up for a bit. But the problem with 3D prints is, while they're very strong in the X and Y axis and the Z axis, or wherever the axis is that your layer lines are, I guess depending on how you think about how your machine is set up, the prints are not very strong, and concentricity is not wonderful either. So what we did in this print was we pressed in 2 bearings on either side of the 3D printed body, and then we turned this aluminum down to a nice comfortable handle on this side, but then reduced the shaft so it goes through those 2 bearings, put a snap ring groove in and a snap ring, and that guy's retained on there, and this spins really, really nicely. Another example actually that you guys have not seen, I might do a video on this in the future. This is an adapter that I made to be able to mount a GoPro on one of these Noga flex arm stands. There's just 2 basically dowel pins on there that are turned down to the exact dimension that we need for this to drop into the holder here on this Noga flex stand. And this guy is a little finicky. You got to kind of open it up a little bit to get this to drop in. There we go. Helps if you're not trying to put it in upside down. So this locks into place there now, and we could put a GoPro on this end, lock this magnetic base onto anything metal, and then we can set this wherever we want it for the GoPro. And this hex wrench rack is a recent project that we did right here on the channel. And this is another one. 3D printing did pretty much all of the difficult geometry for us and kept the cost of this project way down. So all the geometry that the hex wrenches drop into is all 3D printed. We use multicolor to label the holes for each one of these wrenches. And this is actually open in the back for additional storage. But when it came to the handle, yeah, I could have done a much bulkier handle up here that was fully 3D printed, but I really wanted something that was going to be easy to grab, reaching over this where I have this on my toolbox, to just grab it and lift it up without worrying about it breaking, because this is quite heavy. So I turned down the shaft that's threaded on the end that goes into the bore on the 3D printed part, and then turned down this piece at the top, just that you had something nice to grab onto. Another one we did was this guy here. This is a magnetic indicator base where the piece that screws onto the back of the indicator was broken, as well as the threaded piece that goes into it was, even when we made a new one of these and pressed it in, it was still crooked. The original piece just was made wrong. So while the indicator back is 3D printed, we made a new threaded adapter to go onto the actual mag base out of brass. Now, all the different parts for those projects that are not 3D printed, the ones that are machined out of metal, are still made right here in my shop. They're made on my 14x40 metal lathe. And every time I use this machine in a video, several of you guys always reach out and ask me questions about this machine, or ask me questions about what lathe I would recommend that you guys get. And if you have the floor space for a machine this size and you have the extra money saved up, this is a great machine to get. I would absolutely buy this same machine again for my scenario here in my shop, but this is a big machine. Let me grab something for scale. All right, there we go. And following with the tradition of the internet, banana for scale. And I still would not consider this to be a large lathe. I mean, they make lathes so large that this entire thing, the base, everything, would fit in the chuck and spin around like a tinker toy. But in the context of home hobbyist shops, this is what I would define as a larger machine. And by all means, if you have the floor space for a machine this large and you have the extra money sitting around for a machine, this size and this quality, absolutely pick one of these up. And if you guys are interested in seeing a separate review video on this lathe, let me know. I would consider doing that. But the number one question I get from you guys is, how about this machine? And you guys all always send me the same machine. It's this machine from vevor. And again, at the time of this video, this lathe is $640, which is kind of mind-boggling to me. I can't imagine how much you're really getting for $640. So I recommend against getting that machine, and I always send you guys this machine from Precision Matthews. This machine, however, is $2,900, which is certainly a big stretch from $640, but I think it's worth it. Well, that's just it though. I think it's worth it. I don't really know, because my experience is with this lathe. So I thought, let's get them both in the shop. Let's actually see what you're getting for your money with each one of these machines, and let's actually try making some parts on each one of these machines. And here they are, and this is exactly how they arrived. I did open up each one of these crates and peer in and just make sure that there does actually appear to be a lathe in each one of these crates, and that it appears to be in one piece, and it does. I don't think either one of these suffered any shipping damage. I guess we won't know for sure till we get everything out of the box. But this is how they arrived here to my house. All right, before we unbox this, let me show you what we're actually going to do on each one of these machines first. So I have put together an assortment of materials that I think, most beginner home machinists would expect to be able to work with in their shop. So we'll start with something very easy. This is just a plain old piece of aluminum bar stock. We'll face the end of it, and then we'll turn it down to some predetermined diameter, and we'll just try and see how close we can get to that number. And by the way, I would say any machine at any price point that calls itself a lathe ought to be able to work with this, no problem. This is a fairly soft material, and it's also not a very big piece of it. We'll try and do the same thing on this piece of mystery steel. I have no idea what this is. It might just be cold rolled. It doesn't have any mill scale on it, so this was either turned previously or might be cold. I'm not sure. But either way, we're going to use the same piece of material for either machine. We'll just flip it around. We'll do the same thing with this larger piece of steel. This is probably going to be a bit more challenging. This is a pretty good size chunk from a diameter perspective. I think this is just regular hot rolled steel. Let's see. This is aluminum. I've got two pieces of this, roughly the same size. What we're going to do is bore a hole through this. We can just drill it with the tailstock, and then we'll bore it to a specific diameter. Maybe we'll try and bore it to the same diameter that we have turned either end of this to, just to try and see if we can get a good fit. I've got a larger piece of aluminum. All we're going to do on this is just try and give it a nice finish on either side. So we'll have one machine face one side of this aluminum, and we'll have the other machine face the other side. We'll do the same thing on this small square chunk of aluminum. Why? Well, this is going to be an interrupted cut, so this might cause some issues on either machine, because as this comes around, our cutter is going to be in the material, then it's going to be in free air, and then back in the material. So this should be a good test. We're going to try and do the same thing on this chunk of mystery steel. Again, that might be a challenge, particularly with it being an interrupted cut and this being steel. So we'll try that. And then one thing that I don't expect either machine to be able to do, but I put it here just to try. This is just also out of my scrap box. I think this is hydraulic cylinder rod, just based on the scratches on the rod. That's what it looks like to me. Also, I did at one point face this on my 14x40 lathe, and the difference in material here, what you're seeing is it's shiny out here because this is hardened. If this is hydraulic rod, which is what I think it is, and that would make sense for the marks that we see here on the end, that first, call it, I don't know, maybe a quarter inch, is really hard. And hardened material is tough to work on a lathe, so I'll be surprised if we get a good result with either machine from this, but I want to try it. And lastly, I talked about how 3D printing is not that great at making parts that are round in the Z direction, and here's an example of that. So this looks great. It is. We could probably chuck this up on the lathe and put a dial indicator on it, and aside from the small seam here, I think we find that this probably runs pretty true. The problem is we can't really put any force on it in this direction. I can break that pretty easy. And I mean, there's not a ton of walls there, but either way, you guys know or if you don't know, if you're watching this and you're not familiar with 3D printing, it's not very strong in the Z-axis because 3D prints are built up one layer at a time. And it's just counting on the plastic, the hot plastic sticking to the layer underneath. Now, we could print this the other direction. This printed standing up on the bed like this. This printed laying down on the bed. The problem is, now we're trying to print something that's a circle, so we have to have supports under it. And I could take these supports off, but we're still going to see that this is not very round because gravity is fighting against us and stacking this material up. Now, the top half of this looks quite good, but the bottom half would not be usable if we were trying to make a round part. However, as a test, I printed a larger cylinder, same thing, laying down on the bed, thinking maybe we can chuck this up and actually get a very precise part. I have done something similar to this before, and I mean, this is a cylinder. This would be perfectly easy to just turn out of a piece of solid ABS or other material that we would actually buy to run in the lathe. But let's say that this is a more complex part. Maybe this is a pulley or has a lot of step surfaces on it. We could still 3D print this, even laying down, and then do the finish machining on it to get everything to the concentricity that we want. So that'll be the last thing we'll try. We'll try turning down either end of this to a smaller diameter and just see how each machine does for that. And this is PLA, by the way. All right, enough talking. Let's get into these boxes. And let's see. Why don't we start with the little guy first? Let me get you guys in the tripod. All right, initial reaction, that has got to be the cutest machine tool I have ever seen. I don't know if that's a positive thing to describe a machine tool, but it looks like somebody took a full-size lathe and just shrunk it down small. Probably going to be easier to go through this on the workbench. Operator's manual, MX-8x14. I think that's a fuse, tiny little glass fuse. And oh, there's a chip tray. You know, when I ordered this, it actually didn't look like it came with a chip tray, but it looks like it did actually come with a chip tray to mount underneath the lathe, which is nice. And that's it. I think all that's left in there is the actual lathe itself. There we go. Yeah, I think that's all right. All right, I need to figure out how they mounted this in the crate and find some tools. And it looks like the way this is attached in here, I thought it was like a screw head down there, but it's actually the bottom of a bolt. It looks like they ran the bolt right up through the bottom part of the crate. These legs stand at the bottom of the crate up off of whatever you set it on. And it looks like that bolt actually drops right through the center of that. So we don't have a lot of room there, but I don't think we need it. We only need the threads of that bolt to just clear the casting. All right, that's one out. It's actually two bolts down here on this end, and these are 10 millimeter. And for lifting, I have a beam up here on the ceiling of my garage, and I've got a crane scale up there as well so we can see what this guy weighs. But yeah, I mean, you could just do this with an engine hoist. All right, and just the weight of the lathe all by itself is 89 pounds. So not that much, and that's, I guess, a pro and a con. I mean, a pro as in you could probably take this up to a second or even a third floor or a walk-up apartment. The con would be, though, generally speaking, the heavier a machine tool is, the more rigid it is, and rigidity is what you want. So we'll see how the weight of this machine plays into its actual usability from a rigidity perspective. All right, I've got this one slid onto the workbench. Let's get into the next box. Okay, looks like the chip pan for this one is actually bolted to the underside of the lid of the crate. Okay, so I can tell you guys, even though the pictures of these machines look really similar, and I think the other one is an 8x16, this is a 10x22, so it doesn't sound like that much bigger of a machine, but this is a much more substantial machine. Not sure what this is, but it seems like it is attached. Oh, we got a toolbox in this one too. We'll open this on the bench as well when we check out the other one. Got some kind of box. Another box all wrapped up. Another box. And another box. This machine also has the optional DRO. You by no means need to have a DRO on a lathe, but it is really a nice to have. And specifically for those coming from the 3D printing world, I think the dimensional accuracy that you can get very quickly working with DRO is going to be very welcome in comparison to setting up a dial indicator for all your different operations. Something else down here on the bottom. I don't think we're going to get that out till we get the lathe out. Is that? Oh, that's cute. I think this is touch-up paint. Okay, it looks like this one's also bolted through the bottom of the crate. I could see one bolt right there, and I could see another one down there on the other end. So let me get these bolts out. I'll get this rigged up, and then I'll bring you guys back for the weight. All right, and this one is quite a bit heavier, 280 pounds for just the weight of the lathe. And I had to rig it up on the webbing in the middle of the casting there, which was not my first choice, but the DRO on the back made it really difficult to get the strap around it. I even tried a spacer block back here and ultimately landed on that. All right, I'm gonna get the crate out of the way, see if I can drop this down onto that hydraulic cart. All right, I got it landed on the hydraulic cart just barely. I've actually got this casting hanging off, but that should be okay. And we're pretty much right up against the handle on this side. So I'm not even sure where I'm gonna put this one because it's not gonna fit on the workbench with the other one up there. So, all right, I'm gonna clear some space. I'm gonna get this off of the hydraulic cart and I'm gonna wipe both of these machines down. They're both covered in the oil and grease that they slather over them to keep them from rusting. So that's gonna take me some time. Let me do that and I will bring you guys back. All right, situation report. Both of these machines have now been wiped clean of all of the rust preventative, like thick spray-on stuff that covers all the metal parts. And this one over here had quite a bit of grit and grime on the ways of the machine and underneath the carriage. In fact, if you move, every time I move the carriage, I find more of it in there. I actually took a picture and it's like a gritty substance. This machine also had some junk on the ways that was kind of stuck into the rust preventative stuff, but it wasn't like gritty metal stuff. It was, I think it was just kind of general factory dust and also maybe a little bit of sawdust from the crate, but I didn't find any metal shavings in here. I did find some in the tailstock. I took the tailstock apart because it felt a little bit gritty, and sure enough, there was some, you know, sort of, I don't know if it was grinding dust or just general metal grit in the tailstock, but I just pulled the quill all the way out, wiped everything down, re-greased it, and it is nice and smooth now. But that's where the fun stops, because both of these machines, unfortunately, have issues that are going to prevent us from using them, at least right away. So starting with this one, maybe you can see I've actually got the fill plug here for the gearbox out, because the gearbox on this machine was completely empty. And you know, sometimes these little sight glasses can trick you. That's what it looked like, and I've had it where there's an air bubble in there and there actually is oil in it, but I pulled the plug out of the side and peered in there. There's no oil in there at all. It's completely dry, and that kind of makes sense because I unwrapped the plastic and foam from all the boxes that were in there, and several of these boxes are completely soaked with oil, and actually the bottom of the crate was completely soaked with oil as well. So there was literally zero oil in this gearbox here in the front, and I fortunately have some of the gearbox oil that I use in my larger lathe, and I put just a little bit in to see if we could figure out where it's leaking out from. And when I first came back to it, because it's been a couple hours, I saw this drip here. I don't know if the camera's picking that up. It probably doesn't want to focus on it. There we go. I saw that drip and I thought, uh-oh, it's leaking from this cover. That's not a huge deal, but it's going to be a pain. Usually these don't have a gasket. It's usually casting against casting, and there's like a gasket maker seal that goes in there, and I thought, maybe they just missed a spot at the factory. But when I looked closer, I see a small stream of liquid. You see that? Hopefully the camera's focusing on that, from the drain bolt for the gearbox. So I think it's actually all just leaking out from the drain bolt, and that's, I don't know if there's like a rubber washer behind this or what, but you can see they closed it, they painted over it, and then presumably then filled the gearbox, and yeah, it's leaking that fast. It's only been a couple of hours and already that much has come out, so it's not hard to believe that over the course of the journey that this thing took across the ocean to get here, that all of that oil leaked out. So I'm gonna have to pull the cap on this one, see if we can figure out how to resolve that leak there. And this machine's got several issues, some more serious than others. The first one is the studs for the side cover. They are so bent that I had to use a pair of pliers to get the top thumb screw off. I think we could probably straighten this in the arbor press. The weird thing is there's no damage to the crate. So they either put them in that bent and then just jammed the thumb screws on, or they bent it, putting it into the crate and then sent it anyway, you know, which is, I'm not surprised. The more serious issue with this machine, though, is take a look at this. There's the electronics for this. There's the motor control board. It's just floating around in there. It's not attached to anything. And you know, I can't imagine that's right. I mean, there's high voltage on this board, and it's not conformal coated or anything. So the high voltage points on that board are not insulated, and this is steel. I think it's supposed to be attached to the back of this panel. There's 2 screw holes here. I'll find some screws and we'll get that reattached. But yeah, I mean, I guess depending on how it's laying in there, maybe if we plug this in, we'd be okay. But yeah. All right, so I'm going to go ahead and fix the issues with both of these machines and then temporarily mount them to maybe some like just big planks of wood or something like that, so we can move on to testing them. Normally you'd bolt them down to a workbench or your work surface, but since we're just testing these machines, I just want to make sure that they're mounted to something you know, that comes out wider than the casting, so that these machines can't, you know, tip forward or backward. All right, let's take a look at the accessories that we got with each one of these machines. So the pile on the left here is the stuff that came with the Precision Matthews 1022V, and the pile on the right here is the stuff that came with the vevor MX-8x14. Let's start with the vevor one first. All right, let's see what we got in the toolbox for the vevor. Got oil squirter bottle. A set of, looks like brazed carbide tool bits. Key for the 3-jaw chuck with spring included that no one ever keeps on there, myself included. Phillips flathead screwdrivers, a couple of wrenches, presumably these cover the various sizes of bolts on there. The other set of chuck jaws for the 3-jaw scroll chuck, a single center. Presumably that's probably for the tailstock, I guess. None for the headstock. Wonder if it even has a tapered headstock. Metal change gears, which is nice. I'm not actually going to pull all these out of this box, but looks like there is a full set of the change gears for hitting the different speeds and thread pitches that machine will do. And there is a set of hex keys down there. And that is it. So some of you are probably already wondering how we're going to do some of those tests, given that this machine only came with that 3-jaw chuck and there's nothing else here. So yeah, I guess we'll be figuring that out. All right, let's take a look at the Precision Matthews pile. I think this is just touch-up paint. I'm not going to open these. I mean, they look like paint cans, and there's the 2 different colors of the lathe on the top, so presumably that's touch-up paint. We have got, actually don't really know what this wrench would be for. Maybe the change gears? Same thing for this one. I don't know exactly what that wrench would be for. Got key for the 3-jaw chuck, again with a spring. Let's pull that right off. Sorting the wrenches. You see there's hex keys in here too. Okay, so here's the same thing, the other set of chuck jaws for the 3-jaw chuck. A metal oil can. Phillips and flathead screws. And I don't know what these are. Probably also related to the different change gears. More of these hex keys. Oh, there's a fuse in here too. I'm surprised that they put the fuse in the toolbox, because it does look like it's a glass fuse. It's not broken. It's an MT2 dead center. Help you for the tailstock. I think both these machines are Morse taper 2 on the tailstock. Okay, so this machine has a dead center for, this must be for the spindle. This is MT4. This is huge. Morse taper 4. So this presumably would go into the spindle for turning between centers. All right, let's see what we got in these boxes. I think we could probably guess on this one since it says quick change tooling system. And that lathe did have a quick change tool post on the cross slide. So this is probably the other tool holders for that. That looks like a boring bar holder. Some of these are probably the same thing. Since there's like a standard tool holder for these that you usually get at least 2 of. That one's got, and I think this is the style that has a groove in the bottom to be able to use it with a flat tool or a round tool. That is our parting tool holder. No blade though. I wonder if we got a blade with it. Okay, this one is a knurling tool, and you can also hold a tool on the back side of that one. Is there anything in this one? Oh, you know what? I wonder, so this machine probably would have come with a regular tool post too. I wonder if that's what's in here. Yep, that's exactly what's in here. And that's probably also what that one other tool was for. Are these square? Yep. Okay, so this is the optional 4-way tool post that you can put on the machine, and that's what that wrench would be. That looked like it went over square heads. It's for the hold down bolts here in the regular 4-way tool post. So we're probably never going to use this, but it is nice that they included it in case we have an instance where, for whatever reason, the quick change tool post is just preventing us from getting something done. Okay, this next one looks like a real mystery. I'm going to guess that it is a 4-jaw independent chuck. Okay, not only is it a 4-jaw independent chuck, but I was really curious about this. If we were going to get another backplate, and it looks like we did. So this is the chuck, this forward part here, and this part in the back is the backplate that would be specific to this lathe. I was wondering if we were going to get another, or if we would have to actually take the 3-jaw off the backplate to switch it. But nope, we got another backplate and the 4-jaw chucks. That is great. All right, next box. This one truly is a mystery. It is just a brown cardboard box. Some bolts, some foam, okay, this looks like a traveling steady rest. It must mount on the carriage. All right, looks like we got another unmarked box. I bet this is the, just based on seeing this, this is probably the regular steady rest. Yep, that is our standard steady rest. We're going to need this. All right, last box. Okay, this looks like a faceplate. Yep, definitely a faceplate, but I wonder, I guess this must just mount directly. I see they have the plug bolts included with this. This doesn't have the same, let's compare this to that 4-jaw chuck. Okay, this looks a little bit different from this, but the bolt pattern looks the same, and they included a set of these plug bolts. So this must mount directly to the face of the spindle. This is for holding stuff that you wouldn't put in a chuck, where you'd clamp work to, almost like you'd clamp work to, say, a milling table. You can clamp to this to do on the lathe. What are you doing? Nothing? Thought I heard music. Did you have music on? Music? No, I didn't have any music on. All right, never mind. Did you tell them about that machine yet? All right, guys, both these machines are ready to go, but there is quite a bit of a story with this one. Let me play you the clip of the first time I turned this machine on. Yeah, so at that point, I almost didn't even keep going with this review, if I'm honest with you guys. But then I remembered, this machine was $650. I'm not entirely sure what I expected. I thought I had set my expectations pretty low. But rather than throw in the towel, I took a step back and I thought, you know what? Let's make this the best vevor MX-8x14 that we can. Because let's be honest, I can already hear you guys down in the comments. I know what you're thinking. I already own a Precision Matthews lathe, and I do not want you to think that I'm playing favorites. I want to show you what both of these machines are actually capable of doing. So I spent about 5 hours completely disassembling this machine, cleaning everything, removing the burrs from everything, relubricating everything, reassembling it, pretty much completely rebuilding the gear train on this machine. The gears didn't even line up. I had to make spacers for 2 of the gears. I had to cut down the spacer for the feed rod for that gear for it to line up. I had to lubricate everything. Now, I wasn't able to fix everything. There are still some issues with this machine that I was not able to correct, or at least that I wasn't comfortable taking the chance of trying to correct them and making the machine completely non-functional and then not being able to finish this review. One of them is the lead screw on this machine. It is bent. It's bent pretty bad. And I could probably bend it back, but I feel like I'm risking breaking it. And if I do that, then we can't use the machine. The other one is the gib strip inside the compound, if you could even call it that. It's just kind of a hunk of steel that looks like they filed in a couple of places. There's no tension setting on the gib strip for the compound slide that yields a movable compound that doesn't loosen up so much that it shakes around as you try and move the compound, which makes the compound more or less unusable. But I don't think we're going to need to use the compound for the tests that I want to do today. There's some other minor stuff as well, like lots of cosmetic issues, like this is split apart here. And, you know, to vevor's credit, I reached out to them and there was quite the language barrier in the first exchange of messages. But I, tried to explain to them that I had an issue with the lead screw. There was a split in the side cover. The studs were bent for the side cover, and that the motor control board was just hanging out in the breeze inside here. And they more or less told me that I needed to tighten the screws. So I wrote them back again and I said, you know what guys, I was able to find some screws to mount the motor control board. I was able to straighten out the studs in my arbor press for the side cover, but I can't really fix the split in the side cover and I can't fix the lead screw. So I actually took a piece of orange electrical tape and I wrapped it around the lead screw and I took a picture. And I put a piece of tape on the side cover as well. And I sent them another message and I tried to just be as clear as possible that I needed those 2 replacement parts. And to their credit, they said they're sending them. I don't have them. It's going to take a while. They said they're making them in China and will be then sending them to me. So it's probably going to be some time till I have them. But to their credit, they did say that they're sending me those pieces. This machine, on the other hand, other than the leak in the gearbox, didn't need anything. From the very first time I pushed that button, it ran silky smooth. And if you guys recall, we can't see it now because there's a side cover on here, but there is a drain bolt on the side of this gearbox. And I thought it was a bolt with a washer. Turns out it was actually a flange bolt, which is great because flange bolts will seal up nice against a gear case as long as you have a seal on them. Well, they had a hard plastic seal on there and they had just over tightened it and the hard plastic seal had squeezed out and was no longer making a seal. I replaced that hard plastic washer with 2 O-rings, one right at just the same as the outer diameter of the shank on the bolt, and then the other one a little bit wider at the head so that I actually have kind of like a double seal. And I tightened the bolt in just enough to squeeze both those washers, and nothing. It is completely bone dry. It hasn't leaked since, and it now has the correct amount of oil in it. I did also reach out to Precision Matthews just to kind of see what they would say, because this machine should not have arrived with a bone dry gearbox. And I let them know that I had already chased it down to the drain plug on the gearbox. They apologized. They offered to send out a quart of the correct oil for the gearbox in this machine. At that point I said, it's not necessary. I have already refilled it with the jug of oil that I had from my other lathe, but I did want them to be aware of it in case it comes up with other machines, and just in case that is something that is happening often from the factory. Yeah, so that sounds just a smidge different out of the crate than the other one did. All right, I'm tired of talking. You guys are probably tired of hearing me talk. Let's make some chips. All right, let's start with this aluminum round bar and these two chunks of aluminum round bar here. So here's my idea. This aluminum round bar is 3/4 of an inch, 750 thou. Let's turn the OD of this down to 700 thou, and let's drill. Well, we'll face both sides of each one of these pieces, one for one lathe, one for the other. And we'll drill and bore a hole in each one of these as close as we can to the same 700 thou that we put on each end of this with each one of the lathes. And we'll see how good of a fit we can get. And I'll mark it so I know which machine is which. Let's start with the Precision Matthews. All right, we'll start by turning off the little bit of end piece here from the previous project. All right, now we'll face off the end. All right, I stopped the camera for a second because I realized you guys can't see what I'm doing. You can probably see what I'm turning just fine, but you can't see what I'm doing down here at the controls. And for example, right there, I went and I engaged the power crossfeed on this machine to face the end of this stock, but you can't see what I'm doing. So let me rig up a second camera so you guys can see what I'm doing here at the controls, as well as what we're actually turning. All right, now we'll turn down the outside diameter of this as close as we can to 700 thou. And I'm not going to worry about a specific depth here. We just want to see if it actually is going to fit in the other piece that we're going to bore. So to do this, since I have a DRO on this machine, what I'm going to do is I'm going to make a cut. I'm going to leave the tool exactly where it was for that cut. We can back it out, but I'm not going to change the distance away from the stock. We'll measure it, and then I can actually enter that measurement into the DRO. And then we can use the DRO to move in the amount that we need to hit that 700 thou. And we'll probably take that in a couple of cuts. Now, as I move our tool further towards the stock and back from the stock, you can see those numbers actually moving. So our target is 700. So I could go right to 700, and I might do that. Let's see. Let's set this at 700 and just see what that cut looks like. Yeah, it's actually not that much to come off. So let's take that cut right at 700. All right, for taking one cut, we got that pretty close. We are 5/10 over or half a thou large on that OD. Generally speaking, you want to take it in two cuts and measure after your first cut, because the amount of material that you're taking off the OD really does affect what your actual measurement that you're at is. The cutting forces change. I'm not going to go through the trouble of doing that on the other machine, so I didn't think it was fair to do it on this machine. But generally speaking, a machine with a DRO, I will take a cut, measure, and then take a couple cuts as I get close, measuring each time, and I can usually hit it within a couple of tenths, but I'll take that. All right, and there is this part done. And that face looks really nice and clean. The OD of this looks nice and clean as well. I did realize I forgot to break the edge on this. I'm going to put this back in the chuck. It's not going to run perfectly true because I've taken it out of the chuck and we're chucking on this OD, but that's okay. For breaking that edge, it's not really going to matter. You do always want to tighten on your marked jaws. They were nice enough at the factory to mark this. That's what this 0, 0, and 0 is. If you line up this 0 on the spindle with this 0 on the back plate, and the chuck is mounted to the back plate there, and you tighten from this spot here on the chuck, that is when the chuck is going to run as true as possible, as long as the OD of whatever you're chucking up on also is actually true. And this is just a piece of high-speed steel that I ground into a nice 45-degree angle. That's the nice thing about having the tool holders for the quick change tool post. It makes switching to the right tool for the job so quick and easy. Okay, looking at the two pieces of material that we had for this next part of the test, and only one of these is for this lathe, so we'll just pick one. We'll go with the slightly larger one since this is the slightly larger lathe. If we face this and flip it around and then put that face against the face of the chuck, we would know we have two parallel faces when we face the other side. The material's not thick enough to do it. This is the thicker piece and it's still not going to be thick enough to do it. So there's really no point in doing that. So I'm just going to chuck it up. We'll face one side, we'll drill it, and then we'll get a boring bar in here and we'll bore it out to that 700 thou that we turned on the OD of the other part. We'll just break that edge quick. All right, you can see there on the DRO, so we were at 705 tenths. I aimed for a little bit over that because we've got to have room to actually slide that part in. So you see on the DRO, I am at 70132, and with my telescoping gauge, I measured 70115, which is really close. That is within 2 tenths, if that is the actual dimension. So I'm gonna go ahead and break the edge on that part because I forgot to do that again, and then we'll see how we did here. All right, here's our two finished parts. You guys have already seen this one up close. The face on this one looks pretty good. Not quite as pretty as the face on our smaller one. I might not have had the right speed for that. And our bore looks pretty good too. It's not perfect. I think that tool could be a little sharper for aluminum, and we were getting a little bit of chip welding. So, all right, so these should be a really, really close fit. Yeah, it's starting in there. Yeah, they're pretty much right on. All right, I spread a little WD-40 on there because the two are kind of galling against each other. I probably should have left more clearance. There is less than a 1 thou difference between the OD of this and the ID of this, which means when we start to put them together, it's not too bad when we first start, but any misalignment, once we've got it in there, yeah, see, we're in about maybe 3 millimeters now, but it is so hard to keep it perfectly straight. You can see we are bottomed out in that bore. It went all the way in. So, all right, I'm going to knock this back off, and let's try the same thing in the vevor. All right, I've run into quite an interesting problem here on the vevor. I thought we'd have a nice selection of tooling to use with this machine since vevor provided a bunch of this brazed carbide tooling. That's what this blue tool bit is in here. And yeah, I figured we'd have to shim it up on this four-way tool post to get to the right height. That's typically what you have to do with these tool posts, but the tool is too high. So I can't shim it to the correct location because it's already sitting too high with nothing under it. If you look at the cutting edge on that tool bit, it should be either at the same height as the center line of the spindle or lower. Generally it's lower, so you can shim it up to the correct height. But this is starting off too high. So like I can't put anything underneath this to get it to the right height. Anything that I shim underneath is going to make it higher. So I guess they must have mismachined something here. I don't know which one of these parts it is. I mean, it could realistically be any one of these. This one, this one, this one, this one, or this one. But they made one of them too tall, too thick, because we can't get down to the height that we need to use these tool bits. My first thought was I could just machine some off of the bottom of this four-way tool post because you know, this is really plenty thick for the cutting forces that we're going to have on this lathe. But I went to pull it off and I realized it's aluminum. The four-way tool post, instead of being steel, they went with aluminum, which I guess maybe is strong enough for this application. It's not going to last particularly long. I would think we're probably going to strip these holes out that clamp the tool in, since it's you know, steel bolts in aluminum. But yeah, I got to see what I have in my drawer that is low enough to use to actually turn in this lathe. Okay, so here's the tool bit that we had in there that we know is too tall. And I thought about it. I guess we could actually machine some off the bottom of this as well. That would probably also work. But I found this in my box of stuff, and I think this is going to be a better choice anyway. This is actually a tool holder that was my grandfather's. He used to work for Kennametal selling tooling. And it looks like he machined the bottom of this one at some point in time in its life, probably for use on his small watchmaker's lathe. And it didn't have an insert in it, but it looked like it was going to be low enough. So I went through my stuff and I actually found a set of inserts for this. So let me get this one in there and find some shim stock and see if I can get this to the correct height. All right, good bit of trial and error and cutting up a bunch of shims, but I think we are at the correct height now with this other tool holder. And I can't get this tool too tight in here. As I tighten down in these bolts, the whole thing's just bending. Like I do not have these as tight as I would like to get them. And I can see this gap opening up here and this side getting narrower. So hopefully this tool holder is going to be okay for this. That's another big advantage of the quick change tool post. You do have to set your tool heights on this guy as well. If I drop this on here, you see that we have a good bit of adjustability for this guy to slide on the dovetails. And this will lock in any position. If I lock this, it'll stay in position. But you notice I just put it on here and I dropped it down, and what stops it is this this knurled nut on here, and this is a threaded shaft. So you spin this knurled nut until you're at the right height, so that it rests. The knurled nut rests on the top of the tool post, and then you lock it down with this nut. So now every time I set this on and lock it in place, it's going to be at the same height. So you only have to set that once. And if I do swap another tool in here, I don't have to worry about shimming it. I'm just spinning this knurled nut until I've got it at the right spot and then locking the tool post down. All right, there's no markings on this chuck anywhere, so I don't think the factory went through the trouble of actually aligning anything so that this guy runs as true as possible. I think they just bolted it up till it looked like it was centered. So this is probably not going to run as true, but that's okay. As long as we have some extra meat on our stock, it's still going to run true. It just might not run true to the diameter that we're clamping on. All right, honestly, that doesn't look too bad. All right, so that didn't clean up all the way. So what that tells me is that the chuck on this machine is not running anywhere near as true as the other machine. I can definitely feel the step here. We took probably, I don't know, maybe 3 thou off this side, and we haven't cleaned up here yet. So that's all right. I mean, we have plenty of material to get down to our 700 thou. But yeah, it's definitely, stock in this chuck is definitely not running as true as the other machine. A little bit tight in here to actually fit the micrometer. All right, so we are at 722 thou. We need to get to 700. All we have to work with on this machine is the numbers on the hand wheel. And it says that they are 1 thou. What we don't know is if that is 1 thou depth of cut or 1 thou off the diameter. Because whatever our depth of cut is, we're actually taking twice that off the diameter. All right, so according to the dial on the hand wheel, we took off 5. We were at 722. Okay, so we are now at 7, I just bumped it, but we were at 712. So it looks like that's depth of cut. So we have to double that for what we're actually taking off the diameter. Let me measure it again and see exactly where we're at. Yeah, we are 7119, so 712. So we need to take off 12 thou, so we need to go 6 on our dial here. That should be on our hand wheel. That should be right. All right, should have been our finished cut. Let's see how we did. Ha! We are, I just saw it flip. I should have locked it. We were at 705/10, so we were pretty much at the exact same measurement that we were at on the other machine. So I'm gonna stop there. Let's get the next piece in there and let's try and bore it out to for this to fit in. All right, I'm gonna have to see if I can move this tool a little closer to the edge. The problem is I still need to be under these bolts because the side of the tool post is gonna hit our material before we get faced to the center. This really is not a great design. Okay, I angled our tool holder in the tool post and I turned the tool post. I think we'll be able to get it now. Let's try. All right, that was harder than I expected it was going to be for aluminum. I couldn't take off more than about 1 thou at a time, or the motor RPM was dropping down too much. And I was spinning in it. Let's see, let me flip it back on. Yeah, I'm at about 900 RPM, so it's not like we're running this thing real slow. That's about the middle of the speed range on this machine. And anything more than 1 thou, and the motor was just slowing down too much. And you guys can't smell it, but the thing smells like it's on fire. So I don't have high hopes for actually doing much with steel on this machine, but I mean, we did get there facing this in aluminum. So, all right, let's get this drilled and bored out. Okay, so this is interesting. I have to extend the quill to 1.25 inches before it's not ejecting the chuck. And it only has, well, it has 1.5 inches of travel on the guide, the markings here. It goes a little further, but the quill needs to be in there far enough to be sturdy enough. Yeah, it's like it's fully out there. We could probably go to about, I don't know, maybe there. So we only have 1 inch of travel on this quill when you actually have a drill chuck in there. Let me see if I have a drill chuck with a shorter tang. This whole thing is super loose too. It doesn't exactly inspire confidence. Okay, that was a little better. That buys us another 1/4 inch, so we'll use this drill chuck in this machine. This is the same center drill I was using on the other machine. Let's flip it around. All right, we're getting so much chatter there, this thing started to walk across the bench. The thing is, if I slow this down, we're asking a lot more of the motor. So let me see if I can find a speed that doesn't set the motor on fire, that still lets us get this drill bit through here. All right, well, that didn't sound too great, and it doesn't smell too great in here either. I don't know that that motor is going to survive all this testing. But I slowed it down to, I think, 250 RPMs until we got at least the flutes of the drill bit in, and then I sped it back up to, I think, like 550, 600, and then just took it easy. And if I pushed too hard, the RPMs dropped right off, but if I kind of kept even, light pressure on it, it didn't bind up. So, yeah, I think we're through. All right, we have a bunch more tests to do. You guys have seen me work the hand wheels on both machines. I'm not going to bother setting up 2 cameras again for any of these, and I'm not going to cover all of it. I'll bring you guys back for the highlights, but if we do the rest of this testing in the same detail that I did this test here, this video is going to be like 6 hours long. So, all right, I'm going to set the 1 camera up, and I'm going to start running through these, and I'll bring you guys back when I got something to share. It's probably one of the nicest finishes I've actually ever gotten on. All right, well, we have got a bunch of finished test results here on the bench, but some of you are probably wondering if I forgot about this large round bar, and I didn't. Let me show you why it's still here. Okay, so for this lathe, there is zero chance that we're going to get a piece of material this big in here. So I have the tailstock all the way over. That is the quill back in as far as it will go and still hold the live center. This is a tiny live center, and we are still pretty darn short. And this material is only, it's actually less than 13 inches in length. Now you might be wondering, well, Rich, it's an 8x14 lathe. Why doesn't it fit? Well, lathes are always measured the distance between centers. That means no chuck on here and no live center, a dead center. So you have basically two just sharp points to spin something between, which maybe we could potentially turn this between centers. I mean, the thing is, they didn't even give us a dead center for the spindle, and I'm not even convinced that there's a taper in this spindle. I haven't even figured out how to get the back plate off of here. I think the back plate may actually be part of the spindle. So this is the chuck, and this is the back plate. There's nuts back here for me to take the chuck off, but it sure looks like the back plate is actually part of the spindle. I don't know, you let me know down in the comments if you guys have one of these 8x14 lathes and you've actually managed to separate the back plate from the spindle. But yeah, there's zero chance we're going to turn this on this machine. And we can't put it down into the spindle because the spindle on this machine is 3/4 of an inch, and this material is 1.5 inches. This lathe, on the other hand, is definitely plenty long enough. We could absolutely turn this in this lathe. And the spindle bore is larger on this lathe. It is a 1-inch spindle bore, which is actually quite a generous size spindle bore for a lathe in this size. But this is 1.5-inch material, so we cannot put it in the chuck and slide it down the spindle. We also can't just do this and tighten it up. It's sticking out way too far. That would not, even if we got this running perfectly true, that would in no way be safe to try and turn this machine on. Now, what we could do is we could find the exact center of this round bar, center punch it, and then center drill it, just even with a hand drill or a drill press, so that we had a center drilled mark in the end of this. And let me grab my live center back from the other lathe. So we could put the live center in the tailstock. And remember, we've already added a hole down here. I mean, we didn't, but in theory we could. So we'd chuck this end up in the chuck. We'd get it running true. We'd bring the tailstock down and put the live center into the hole that we've already put in here. Now at that point, we would basically be set up to do turning on this material. We could turn the outside diameter, but if you remember what I said, we were going to face this material first. Well, we still could face this material in this lathe. We could turn a true section on the outside, say, maybe in this region here. Let's pretend that we've done that. Now, hold on, let me grab something else. We would then drop this down onto the machine. This is the steady rest, if you remember from the unboxing. This gets bolted in place, but I'm just going to set it on here for now. Now, where these brass fingers are, we would put our stock back in. We'd get it running true in the chuck again, and then we position this so that the area that we turned to run true with the lathe was where these brass fingers were. We tighten the fingers in, indicate that, get that running true, oil that up, and then we could face the end of this stock because the chuck is taking care of keeping the stock from moving back and forth this way and applying the torque to it to turn it, and this is keeping the stock steady so that we can face the end. And now we have to face off substantially more because, remember, we started by drilling a hole in the end, center punching it and drilling a hole in the end so that we could even machine the true section on the OD so that we could put the steady rest on so that we could true it up. You get the idea. It's probably a half-hour effort to do that. And here's the thing. If you buy this lathe or a lathe this size and you don't envision turning material over 1 inch in diameter this long on a regular basis, that's not going to bother you. If you have to do that once or twice a year, I'm sure you'll be happy that you're able to do it, that they provided you a steady rest to do it, that you can go through those steps and get it done. But if you want to turn stock this size on a regular basis, just look at a bigger lathe. Let me show you the steps involved in facing this material on my 14x40 lathe. This lathe has a 2-inch spindle bore, so we can just slide the stock right down the spindle, the same as we did those smaller pieces of material in the two smaller lathes. And we're done. If you blinked, you might have missed it. I don't even know why I did that in 2 passes. We certainly could have just taken that in 1 pass. All right, let's take a look at our results. So, see, we already took a look at these. The Precision Matthews one, great fit. It's actually, it gets stuck on there. It's such a nice, perfect fit. The vevor one, the OD honestly looks pretty good. I mean, it's not as nice as the side that was turned by the Precision Matthews machine. Those marks are galling from me trying to put it in there. But this side, you can see, it's not quite as consistent. You can see that there was some chatter in the finish just from the tool post on that machine moving around. And the bore was really, really hard to do. So the tool post on that machine, it seems perfectly rigid for turning, or rigid enough. I mean, I'm not going to call that a bad result. Honestly, I think that looks pretty good, and the facing looks really good. But boring, the cutting forces are in the other direction, and it was just all over the place. It was completely inconsistent. And no 2 cuts, even if I tried to have the same depth of cut, yielded the same amount of material actually off of the diameter of this bore. So we ended up, I think, 4 thou oversized, which is honestly pretty bad, but it looks okay. The steel, I was surprised how poor the vevor performed here. I knew it wasn't going to do well. Let's take a look at the Precision Matthews side first. I mean, that looks pretty darn good. I'm not going to say that is the best surface finish I've ever seen in steel, but it's certainly nothing to complain about. It looks pretty darn good. The vevor, this is after I had the second go at it, because I got such a good result on the Precision Matthews machine. I thought, you know what, let me try again, especially since I had actually turned over the result that we got on the vevor since it was so bad. So I tried turning the other side, and this is the best result I could get. And, you know, from an appearance perspective, part of it's not bad, but if you can see the light bending there, and the finish, what's going on is the diameter is not consistent. I can feel it with my finger. It feels like it just feels like it has like waves and ripples in it, because to get the cutting forces required to even remotely get a decent surface finish on this material, the whole machine was flexing. I could actually see the machine flexing. It would flex away and then kind of come back and flex away and kind of come back, and that's why you have all this waviness in this. It's one diameter here, another diameter here, another diameter here, and another diameter here. So yeah, really surprised just how poorly that machine performed in steel. I did not bother turning this on both machines. The purpose of this was really more just my own personal curiosity to see if we could actually do this. I think both machines, you know, to be fair, would have been capable of turning this. We turned this on the Precision Matthews, but so here's where we initially started. This was the print that was laying down on the bed. This is just plain old PLA. And my idea was to see if we could turn this into a piece of material with actual true dimensions. And face looks really good. Some interesting, you know, kind of wavy effect in there from the layers in the material. And same thing on the diameter. Like, it feels really, really smooth. I can't feel any difference as I spin it around, but you can certainly see a difference in it. In fact, it actually looks kind of cool. I wonder what that would look like with some mineral oil on it. I mean, to somebody, it's probably art. Yeah, I mean, the goal here was to see if we could do this, and this is a really simple shape. All we did was just turn it into an accurately dimensioned cylinder. But imagine if this is a much more complex part, and we can 3D print the rough shape and then turn all the features on it in the lathe. So that worked really well. I think we're going to be revisiting this. I think in the future, we'll try this again on a more complex shape. So I didn't even mark this because only one machine was able to do this. To be fair, I think the vevor machine would do this if we were able to, say, put the larger chuck from the Precision Matthews machine on the vevor, which would technically fit if we had a backplate for it, if we could even figure out how to get the chuck off of that vevor. But the chuck on the vevor just simply did not open up wide enough, even with the external jaws, to be able to hold this material. And this is 4-inch round. And the surface finish on this is just absolutely beautiful. The only marks on this are my fingerprints and the scratches that I put on it trying to put it in the chuck on the vevor. This is probably one of the nicest surface finishes I've ever got in aluminum. I mean, that is just absolutely gorgeous. We also got a great surface finish on the interrupted cut for the square stock on the Precision Matthews machine. This is aluminum. That is I mean, I was about to say equally as nice, but it's not quite, because where we had the interrupted cut, you can see there is probably a little bit of chatter there just from the material pushing the tool post away. It still looks really good. I mean, you have to look for it. Unfortunately, we could not face the other side with a vevor because the machine only came with a 3-jaw chuck. You can't hold a square piece of material in a 3-jaw chuck. Same thing for the steel. We were only able to run this test on the Precision Matthews. The surface finish on this is not quite as nice. It's good, but I think I could probably get a better surface finish on this in my larger lathe. Again, because of those interrupted cuts, well, partly because of the interrupted cuts, partly because I was just not able to push this material hard enough to break the chip, and we were just dragging chips around on it. Maybe we could have, but it was making me nervous. Even this is a heavy enough piece of material to hold in a smaller 4-jaw chuck and spin it at any kind of speed. I'd feel much more comfortable pushing the speed of this a lot higher in a larger machine, but I think I was turning this at maybe 450 RPMs in the Precision Matthews 1022, and yeah, that's still a good result. It still does look really good. This is probably the most surprising piece of material up here. I intentionally chose a material for this test that I expected both machines to fail at, because this was pushing my 1440 when I faced it. And I don't know, maybe I didn't have the right tooling when I ran it on that machine, because I did not expect the PM-1022 to be able to turn this material. I think this is induction hardened hydraulic rod. You can see the difference in the finish in the outer diameter, and that machine did it. And honestly, the face that we left on this in the PM-1022 looks nicer than the face that was on this that I had turned in my 1440. So again, that might come down to tooling. I'm sure the 1440 can do equally as good a job as the 1022. But again, the point being, the 1022 turned that. It turned that hardened material without really any complaint at all. I mean, I heard the motor labor a little bit, but not much. Here's both these machines in the same frame so you can get an idea of how they compare to each other. This is an 8-inch swing machine, and this is a 10-inch swing machine. That doesn't sound that different on paper, but the reality is they're pretty different sized machines, and there's a lot of other big differences in these machines that are not immediately apparent if you don't know what to look for. Some of you probably already noticed a few of them. Let me show you. So we already talked about the tool post on the machine. I mean, that's a big one. You could put a quick change tool post on this lathe, and that would alleviate that issue. But did you notice that there's no markings on the hand wheel for this axis on this machine? There's nothing. So if you want to know how far you're moving in this direction for any type of precision, you've either got to do that movement with the compound, but as we established, the compound on this machine is basically unusable, because if you tighten the gibs enough to be tight in any one position, when you move it, it either gets so tight it's stuck, or it gets so loose that it flops around. How about the lead screw on the machine? Did you notice the difference? It's not just the pitch and the thread between these two machines. There's another big difference, and this machine's actually hiding that difference right now, but I'll show you in a second. So this machine does have power feed into this axis. It's done by engaging the half nuts, which are typically used for threading. There's two pieces in there that when I turn this knob, they basically pinch down on that thread, and they have the matching thread on their faces and basically allow this guy to travel with the pitch of that lead screw as it's turning. It does not have power feed in this direction. But the other big difference is you're using this lead screw for power feed, not just threading. And it's a fine pitch thread, so this is going to wear out fairly quickly. Now, if you're really diligent and you keep it oiled and clean regularly, you're going to get a fair amount of use out of it, but it is still going to wear out fairly quickly. This machine, right away you notice the thread pitch is different. This is actually a completely different kind of thread. It is a much more durable thread. But let me turn the spindle up here. I don't know if you guys happen to catch this in watching this machine, but in addition to being a lead screw that we do use for threading, did you notice it has this slot in it? That slot actually drives a dog inside here that transfers the power from this lead screw to provide our power for the feeds on this machine. And this machine will feed this way, and it also power feeds in this direction and this direction as well. That you engage that with this control here. Now I still have this control here, and that does a very similar thing to that machine. So for cutting threads, I do use this, and this has a set of half nuts that come down on this, again, much larger, more substantial lead screw, but it's not using the threads on the lead screw for those power feeds. So you're not wearing out the threads on this with those power feeds. Again, that torque is being transferred from the slot here in this lead screw. How about the ways of the machine? Did you catch that? So if you look at this machine, we have a single flat surface over here, and then we have a flat surface here and a V here. And if we look at our saddle, that's this piece here, the saddle rides on that V and it rides on the flat over here. And if we look at the tailstock, it rides on the same thing. It rides on that V and it rides on part of that flat over here. Well, that's not typical for a lathe. It's typical for these super tiny ones, but that's not normally what you have on a lathe. So if you look at this lathe, you notice we have a large V, a flat, a small V, and another flat. And if we look at the carriage, it rides on this large V and this flat over here. If we look at the tailstock, it's riding on the other set of V and flat. And that's done for a number of reasons. One of the big ones is wear, so that those surfaces wear separately. You also have a reference between those two surfaces should the machine ever need any reconditioning. On this machine, I can also reverse the feed with this knob up here on the front. So in this position, if the spindle is running in forward, the carriage is going to move this direction under power feed, and my cross slide is going to go into this direction under power feed. If I reverse this, those feeds are going to run opposite. So if I'm, say, turning, cutting into this direction, that is how I get that feed. Now, if I run the spindle in reverse, obviously the feeds run in reverse too, but that doesn't help me if I'm still trying to turn off material. I just need to feed in this direction. You can do that on this machine too, and let me show you how. It's this thing here, and it's, even though I fixed this cover, it was out of alignment, it was actually, this was bent over, it's still kind of in the way. You have to pull this out, or no, is it push in or pull out? It's pull out, I think. Yeah, it gets stuck on here. You have to pull this out, and then this whole thing moves to another position down here. It basically moves this gear from one position to another, and now the feed on this will run the other direction. So it's nice that you can do it, but you've got to take the whole side cover off every time you want to change direction. We can also control the rate of the feeds right on the front of this gearbox. That's what this A, B, and C is. We have a slow, medium, and fast, even though we only use the one rate of feed in all these tests, and you'll probably find yourself in the middle range most of the time as well. But this is a oil-filled gearbox, so all three speeds as well as the reversing gears are bathed in oil and are going to last a long time. On this machine, we can change the rate of the feed as well, but we have to do it by changing out these gears. Now, to be fair, we're changing out gears on both of these machines for cutting threads. But it's not that often that you're cutting threads on a lathe. I guess it depends on what type of work you do. I mean, I probably use my lathe 20 times for something else before I happen to be cutting threads, or more. On this machine, even if you want to change the feed rate, you still have to change the gears out because it's the same lead screw that cuts the threads that's also doing our feeding, so it makes sense. We would have to change the gearing to get different rates of feed as well. The other one that I can't show you is inside this spindle, or really inside the headstock that the spindle is riding on. There's two just plain old ball bearings. There's one on this side and one on this side, and they gently tighten in on those ball bearings so that the spindle does not walk back and forth. That works okay, but that is not how the spindle in a machine tool should run. I mean, forget about a lathe. Even any high-end piece of equipment with a decent spindle is not going to run in ball bearings. It runs in angular contact bearings. And that's what this machine has. They're more similar to like an axle bearing where you have large rollers that contact a flat surface on either side, and they pull together to give you a tremendous amount of accuracy both in this direction and in this direction. And if you're wondering if you could start with the 8x14 lathe and get it up to the general capability set that we have with the 1022 lathe, I did a cost comparison on that just to kind of see where it's at. So the lathe itself is certainly way cheaper at roughly $640 versus roughly $2,900 for the 1022. But to add the things that the 1022 comes with that you're going to need to use in the general course of just making parts. So if we add in the dead center, 2 back plates, because you're going to need one for the faceplate and the four-jaw chuck. You're also going to need to pick up that faceplate, the four-jaw chuck. There's no steady rest. There's no follow rest. Now, they're not that expensive to pick up, but these things do start to add up. Quick change tool post, similar quality one to what's included with the Precision Matthews machine, is about 200 bucks. And the motor upgrade, I threw this on here because in testing that machine, yeah, it's severely underpowered. It might be able to do steel with a bit more rigidity and a more powerful motor. You could probably get the rigidity by maybe getting rid of the compound. A compound is not something you use that often on a lathe. I mean, if you want to cut tapers, sure, you need it, but otherwise you could get rid of that compound, replace it with a solid tool post, upgrade the motor, and do all these other things. And, sure, you're working with smaller material. There's still lots of other things that are going to hold you back, like the bearings in the machine, etc. But you'll get about $13.51, which is getting darn close to half the cost of the 1022V. And every time you use the 1022V, it's going to be an enjoyable experience versus fighting with this thing that has sucked all of your time and money out of your wallet trying to get it to a useful state. So what do I like about these machines? What could be better? And who are these machines for? Let's start with the Precision Matthews. I think this machine is for your average hobbyist. It's not marketed to someone that is keeping farm equipment going. It doesn't really have the capacity for that. And it's probably undersized even for typical, like small auto work. But it's a perfect size for someone doing hobby type work, doing functional stuff or doing repairs on small items. And it doesn't take up that much space. I mean, I added this right to my bench here and it fits just fine. Now, there are some things that could be better. It's a small gripe, but this display here for the speed, it's loose in there, it rattles around, and it's flat on the back, but it's mounted on a curved surface. Like, this is something that, honestly, a functional print could probably resolve pretty quickly, but it just feels cheap. I also think that, I know there's not room in this machine for a gear cutting box on it. So, much like we have this ABC for the speeds on this machine, there's no room on this gearbox for another set of knobs to control the pitch screw that we're cutting. I get that. That's what you get with a machine this size. However, we're living in the future already. I think the first company that comes out with a machine in this size, in this sort of size weight class, that comes with an electronic lead screw standard is going to be taking it to the bank, because there's really no reason to have all those change gears on the side anymore. Yeah, it adds an expense, sure, but it's not like the year 2000 anymore. These components are cheap. We can add an encoder to this machine, and we can add a servo drive or a motor down here to drive the lead screw, and we can cut whatever thread pitch we want just with a touch of a button. What about this machine? What do I like? What do I dislike? Who is this machine for? Well, from a marketing perspective, I think it's for everyone. I think they're hoping that you don't really pay attention to the details, that you don't realize that the machine you're getting is a lot less capable than other machines that look comparable but cost quite a bit more. What do I like about it? Well, that's actually pretty easy. I think it's almost a portable lathe. It's so lightweight, even screwed down to this base, I think it's only 100 pounds. I mean, I could roll this hydraulic cart over and just slide it right onto the tailgate of my truck, I guess, and go make parts somewhere, as long as it's within the capability of this machine. That is kind of neat. And it's, it's just kind of cute. But that's where it ends. What do I not like about this machine? I guess kind of everything. It's not rigid enough to do any real work on. The way the power feed works on this machine, I think that's just a mild steel lead screw, which means it's not very long for this world, especially if it gets used for power feeding. It'll probably continue to work for power feeding even when that lead screw is really, really worn, but then you're not going to be able to do any threading on it. There's no dial on here to even know how far you're advancing in this direction. The tailstock is so loose that, you saw what happened when we tried to drill holes. It's got an aluminum four-way tool. I mean, yeah, you guys watch the video if you're still watching it at this point. There's not a whole ton to like here, yet at the same time, it did pretty well for aluminum. Like if you just want to do small parts out of aluminum or brass, I guess you could do it with this, much like you could continue using that really old worn out screwdriver in your junk drawer in the kitchen that is never the right one, and you should just go to your shop and get the real one. I also want to say thanks to both Precision Matthews and vevor. This video would not have happened without the support of both these companies. Now, I wasn't paid anything to make this video. However, I couldn't have made a video like this if I had to buy both of these machines. And interestingly enough, this video actually started out with a marketing representative, or somebody at least representing vevor, that reached out to me and offered me this machine. And I worked with them for a little while, and I felt like we had reached, some terms. And, I thought, all right, next I'll reach out to Precision Matthews and see if I can work out something with those guys. And then it got complicated, much like this machine in general. vevor at the 11th hour, I'm going to say, in the, sort of the negotiations of how things were going to work, said that they wanted to see the video first before I published it if they were going to send me a machine. And I flat out refused to do that. You guys know I've reviewed things on this channel before that companies have sent me, and that is really, one of the most core principles that I stand by in reviewing anything that gets sent for use here on the channel. If a company wants to see the video first, I have no time for that. These videos take a tremendous amount of time to make, and I don't want to remake the video, and they know that. So they know that you are going to go out of your way to make sure that there's nothing in that video that they're not going to like, because you don't want to go through the effort of remaking the video. Now, when I reached out to Precision Matthews to talk to them about what I had in mind, there were still some details to work out, things like logistics, but they did not want to see the video before I published it. I specifically asked because I was not interested in going down that road, again, wasting a bunch of my time to find out that they were going to want to approve the review video before I posted it. They had no interest in seeing the video before you guys do. They're probably watching it now. You might find it down in the comments, but they have not seen this video. They have not gotten any feedback from me or any information about how this video is going. They're seeing it for the first time, just like you guys. I guess vevor is too, but they're probably not actually watching the video, because if you haven't figured it out, I did not accept that machine under the terms of showing them the video. This was also a much cheaper machine, to be fair. I just ponied up and bought this machine. I figure, I could probably resell it for more or less the same that I paid for it. I also wasn't sure if I'd be keeping this machine around. I have had kind of in the back of my head the idea that it would be neat to have a smaller machine that I could have a collet chuck set up on, and maybe even do an electronic lead screw conversion. So let me know down in the comments if you're interested in seeing that. I'm pretty sure I'm keeping this machine. I've actually kind of fallen in love with it. As much as I like my larger lathe, this one is more convenient for smaller stuff, particularly because of the variable speed. I found when I'm facing stuff, I can just turn the speed up as I get closer to the center and still get the same consistent surface finish. Guys, as always, thanks for hanging out in the shop with me for this week's video. I know this was a long one, so if you made it through this whole video, give yourself a pat on the back and do me a favor. Let me know down in the comments, what did you like? What did you not like? What surprised you about these machines? And did it potentially influence your opinion? I'm really interested to hear. I know some of you guys probably have zero interest in metalworking, but I know there's a good portion of you guys that do, because it really does sort of fall into that toolbox of things that you need to be able to have the capacity to do in your shop if you're serious about making and designing your own stuff. 3D printing is a tremendous process, but there's certain things that plain old subtractive manufacturing, doing work on a lathe, turning and milling, it's just not ready to replace yet. If this is your first time here on the channel, we normally do 3D printing. I come up with a design to either fix or improve something. I share the STL, walk you through it. So check out some of the other videos on the channel if you're interested in that sort of thing. And if you like what you see, hit that subscribe button. And guys, if you do, I'll see you next Friday.